Good morning to one and all. Myself, Nagajyothi, working as an assistant professor in Department of ECE in Mlritm College. So, in the last sessions, we have discussed about the first module of a control system, how to determine a transfer function for an electrical system as well as for a mechanical system. Not only finding the transfer function for electrical and mechanical systems, we have also discussed about the signal flow graphs as well as a block diagram reduction technique. So in case of second module, we are going to discuss about what is meant by time response analysis, what is the importance of a time response analysis, and for different types of inputs, how the system is going to behave. So the outline of the course is introduction to the time response analysis and what is meant by a time response and what is the use of time response and which type of inputs we are applying for the system. As we know that for any system, in order to determine the output, we need to give some sort of input. So in case of time response analysis, here we are going to give some sort of test signals. So what are those test signals? How to represent those test signals in graphical manner as well as in mathematical notation. And in our syllabus, we are having time response analysis for first order system as well as for the second order system. But in this lecture, I'm going to give you time response analysis of first order system. So the first thing is what is meant by a time response. So time response is defined as output of a system when subjected to an input. So here the input should be a function of time. So here whenever I'm saying input is a function of time, that itself indicates it is continuously varying with respect to time. For each and every instant of time, there will be change in the input. Depending upon the changes in the input, the system should be reflected at the output. So whatever the input which we are applying for the time response, it should be function of a time. So what is the reason why we need to go for time response analysis? This time response analysis will give you an idea how fast the system is responding for a given input. So in case of time response analysis, it involves the examining of how the system output is going to be changed for a particular input within a predefined manner. And basically this time response analysis is used for evaluating the performance of a system in terms of its stability. As I've told you that we can say that whether the system is slow or fast by understanding the concept of time response analysis. Now let me assume that I have given the input for a system at t1 instant of time. If the output which I am getting is T2. So if the deviation between the T2 and T1 is very less, that itself indicates the system is very fast. So the fastness or slowness of a system can be determined by using a time response analysis. Basically, this time response analysis consists of two parts. One is transient response and the other one is steady state response. So if we take a simple example, let me assume that I'm switching on the fan. The fan is having the maximum speed of 5 volts. So whenever you are switching on the fan will not rotate automatically to the maximum speed, but slowly it will increase the speed. So the time taken for the fan to reach from 0 to the maximum value is nothing but called as a transient response. After reaching to the maximum value, it will continue its speed in the same level. That is nothing but called as a steady state response. So in general, I can say that a time response is a summation of transient response as well as a steady state response. If we want to represent the same thing in a graphical manner, here I have given some sort of input and the output is varying with respect to time. So if you observe here, the output is basically at 0, but from 0 it is reaching to the maximum value. Once it has been reached to the maximum value, it is oscillating, means the output is slowly decreasing and it is making constant. So how much time the output is taking to change from 0 value to the final value, and after reaching to the final value still it is oscillating, this particular response is called as a transient response. And wherever the output is constant, that response is called as a steady state response. So in general, the time response analysis can be represented as Ct of t. This Ct of t is nothing but a transient response, and Css of t is nothing but a steady state response. Now if we observe here, initially the output of a system is 0, but whenever you are giving some sort of input, it is reaching to the maximum value. In general, the maximum value is, if you are representing in terms of percent, it will be 100%. If I am taking in terms of values, let me assume that the maximum value is 1. Means if I am giving any input, it has to reach to only 1. But in this case, if you observe here, the output is reaching above the maximum value of 1. So whatever the deviation which is present, 1 and the maximum value, this deviation is called as a maximum overshoot, and the time taken for a system to reach to the 50% of the maximum value is nothing but called as a delay time. So in case of a transient response, we are having some parameters like delay time, peak overshoot, peak time, and settling time. This we are going to discuss about all these parameters in the next section. But meanwhile, just remember that transient response plus steady state response will give you the time response analysis. So here, as I told you that for any system, in order to know how the system is reacting, means whether the system is a slow system or a fast system, we need to give some sort of inputs. So basically, whatever the type of the inputs which we are applying for the system is nothing but called as a test signals. So the basic test signals which we are using in our syllabus is nothing but an impulse response, impulse input, step input, ramp input, parabolic input, and a sinusoidal input. And please remember, all these inputs are continuously varying with respect towards the time. So coming to the first standard test signal, which is nothing but an impulse input. So here we can define an impulse input, that is the signal is present only at t equal to 0 and elsewhere. For t less than 0 as well as t greater than 0, the impulse value, the signal won't be present. So we can represent that it is sudden change in the input. This is a graphical representation of an impulse signal where the signal is present only at t equal to 0, and for t greater than 0 and t less than 0 there won't be any signal. And the notation for the impulse signal is nothing but an delta of t, and the mathematical notation is, as I have told you, that all these are the test signals which we are giving as an input for a system, that is nothing but r of t. So here r of t is nothing but an input signal, and as it is an impulse signal, impulse is del of t, and it is equal to 1 only at t equal to 0, and for other cases the value is 0. And all these things we are going to find out for a transfer function. As already we know that a transfer function is nothing but a Laplace transform of output by Laplace transform of input, assuming the initial conditions as 0. So as I need to calculate the Laplace transform of output and input, here the Laplace transform for the impulse signal is nothing but an 1. Coming to the second type of signal, which is nothing but a step signal. So in this step signal, we are having a constant amplitude for the positive values, and there is no values for a negative values. And if you are assuming that amplitude of this step signal is 1, then it is called as a unit step signal. So it is having a constant amplitude, and it is present only for the positive. So that is the reason this can be represented in a mathematical way as amplitude A for t greater than or equal to 0 and 0 for the other cases. And the Laplace transform for a step signal is nothing but A by S. If you assume that amplitude of this step signal is unit step, then we can write down it as 1 by S. Similarly, coming to the third step signal, which is nothing but a ramp input. In case of a ramp input, a signal which is linearly increasing with time is nothing but called as a ramp signal. So in this case, at time t equal to 0, the amplitude of the signal is also 0. Let me assume that at t is equivalent to 1, the amplitude will be 1. At t is equivalent to 2, the amplitude will be 2. So the difference between the time axis will be same is equivalent to difference of this amplitude. That is the reason it is called as linear. As it is increasing, it is called as a linearly increasing. And the notation for the ramp signal is A into T. Here A represents the amplitude of the signal at each and every instant of time. And as it is represented only for the positive cycle, for T greater than or equal to 0, amplitude is A, and for T less than 0, amplitude is 0. And the Laplace transform for a ramp signal is nothing but an A by S square. Coming to the fourth type of a test signal, which is nothing but a parabolic signal. So what is the difference between a linear, that is in previous ramp signal, as I told you, it has a linear signal. There is the deviation between the time and the amplitude is same, but in this case at 0 the amplitude is 0, but at t is equivalent to 1, the amplitude will not be 1, it may be either 0.5 or less than that. So here, as the deviation of the time is not is equivalent to deviation of the amplitude, it is nothing but called as a parabolic signal. So in general, we can say that rate of change of velocity is nothing but an acceleration. Acceleration can be represented in terms of a parabolic function. And the mathematical notation for this parabolic signal is nothing but at square by 2. And in this graph, if you observe here, the parabolic signal is present only for the positive side. So it is for t greater than or equal to 0. And for negative side, as there is no signal, it is represented as 0. And the Laplace transform for this parabolic signal is represented as A by S cube. The last most important standard test signal is nothing but a sinusoidal signal. In general, a sinusoidal signal is represented with, this is a sine waveform in which the mathematical notation can be represented as A sine of omega t plus phi. A sine signal consists of basically three parameters. One is an amplitude A, and omega is frequency of the signal, and phi is phase of the signal. So in this example, I have taken the phase value as 0. I am least bothered about the phase, but I am giving some importance for the amplitude as well as the frequency of the signal. Now, coming to that, the actual concept base for this session is nothing but time response of a first order system. So first let me tell you what is meant by a first order system. As I told you that the transfer function is represented with Laplace transform of output by Laplace transform of input, assuming initial conditions as 0. So the transfer function consists of two parts. One is a numerator part followed by the denominator part. Whatever the roots which you are equating, the roots which you are getting, numerator roots, those are called as zeros of the system. Similarly, the roots of the denominator part will give you the poles of the system. In order to say the system is control system, that itself indicates we need to have an idea of stability. We can say that a system is stable if the poles are present to the left half of the S-plane. So here the number of poles, so the denominator part, if the denominator part S value is power 1, that itself indicates it is a first order system. So here in order to represent or in order to calculate the time response of a first order system, as similar to that of the previous case, I have taken a system with a feedback of unity feedback. So here R of S is an input signal. In general, in the control system, it consists of some excitation, which is nothing but an input, and it consists of some output, which is nothing but C of S, and an error signal, or which is used in order to minimize the deviation between the reference value and the actual value at the output. And this is forward path gain, and this is a feedback path where h of s value is equivalent to 1. So if you observe here, this forward path here, s value is power 1. That is the reason it is called as a first order system. As we know that here it is having a feedback path which is of negative, that itself indicates we are having a negative feedback. In the previous sessions already we have discussed and we have derived how to find out the transfer function for a negative feedback. So the generalized equation for a negative feedback control system is nothing but g of s by 1 plus g of s into h of s. But in this case, h of s is equivalent to 1 as it is a unity feedback system. This can be written as here g of s is nothing but 1 by st. So substitute this instead of g of s as 1 by st. So 1 by st by 1 plus 1 by st. So if you simplify that, you'll be getting 1 by 1 plus st. So if you observe here in the denominator part, the power of s is equivalent to 1. That is the reason it is called as a first order system. The power of s is 1 in the denominator term. Hence the above transfer function is of the first order system. And this can also be written as I have told you that the transfer function is nothing but C of S by R of S. If I want to calculate only the response, here response is nothing but output. So here C of S can be written as R of S into 1 by 1 plus ST. And here this R of S is nothing but a Laplace transform of the input signal R of T, and C of S is nothing but a Laplace transform of output signal C of T, and T is nothing but a time constant. So in order to determine the time response of the first order system, in the previous case, I didn't assume any type of the input signal. Just I have assumed it as R of S. Now, if I'm assuming that input signal is either an impulse signal or a step signal, how to determine a response of a first order system? So the basic step is just apply the Laplace transform for the input signal. Then as already we know that the response of first order system can be written as C of S equal to 1 by 1 plus st into R of S. Substitute this R of S value. If it is impulse response, substitute it as 1. If it is unit step, represent it as 1 by S. If it is parabolic, represent it as 1 by S cube. So depending upon the type of the input signal, just replace this R of S value and apply the partial fraction. And after applying the partial fraction, apply inverse Laplace transform so that you'll be getting the output in terms of time domain. So now let me assume that the type of the input signal which I'm applying is an impulse response. So as I told you that the first step is I need to calculate the Laplace transform of R of T. So here R of T is nothing but an impulse signal. So for the impulse signal, I am representing it as del of T. As just I have told you that the Laplace transform of an impulse signal is 1. So instead of R of S, just I need to replace it 1. So already we have calculated this C of S is equivalent to R of S into 1 by 1 plus ST. This R of S need to be replaced with 1. So I'll be getting C of S equal to 1 by 1 plus ST. This is in the Laplace domain. But if I want to convert this into a time domain, I need to apply the inverse Laplace transform. So I'm rearranging these terms and I'm applying partial fraction method, and I'm applying the inverse Laplace transform. So if you apply the inverse Laplace transform, C of S can be written as 1 by t e power minus t by t. So here it is 1 by s. This is 1 by t. This 1 by s plus 1t can be written it as e power minus t by t. And as if you observe this, it is exponentially decaying function. So if you are giving the input signal as an impulse signal, the output response is decaying to exponentially decreasing to 0 with a time constant of 1 by t. So input is impulse, but output is exponentially decaying value. Similarly, let me consider how to find out a first order system for a step input. So this is the impulse response of first order system. Here I have applied the input as impulse. Now let me assume that instead of impulse input, I am applying it as step input. So consider the input as a step input. So the step input is nothing but, in this I am assuming that it is unit step. Unit step itself indicates the amplitude of the step signal is 1, and the Laplace transform for the unit step signal is 1 by s. As we are having an equation of a first order system, this r of s need to be replaced is 1 by s because of unit step. So I have replaced this r of s with this. So this can be written as a by s plus b by 1 plus st. That is nothing but applying a partial fraction. So this can be written as a by s plus b by 1 plus st. And we need to calculate what is the value of a and what is the value of b. Value of a and value of b can be determined by using a partial fraction. Just cross multiply this, so you will be getting s into st plus 1 is equivalent to a into st plus 1 plus bs. Equate the terms. So 1 is equivalent to, equate the terms and equate the s powers to both the sides, so that you'll be getting a value is equivalent to 1 and b value is equivalent to minus t. Substitute the same a value. As I got a value as 1, this can be written as 1 by s and b value as minus t minus of t by 1 plus st. This is after the performing of partial fraction. The last step in determining the time response is nothing but, this is in S domain, which is in Laplace. I need to convert into a time domain by applying an inverse Laplace transform. So the inverse Laplace transform of 1 by s is nothing but 1, and this can be written it as 1 by 1 plus st is nothing but e power minus t by t. So here 1 by s minus 1 by 1 plus s plus 1 by t. This 1 by s inverse Laplace transform is 1, and the inverse Laplace transform for this one is e power minus t by t. So as whenever small t is equivalent to t, I'll be getting 1 by e power minus 1. That itself indicates 0.632. And already we know that this capital T is nothing but time constant, and this 63.2% itself indicates the time required for the output signal to reach to the steady state value or the final value. And this, what is the importance of this time constant is, this time constant will indicate that how the system will reach towards to the maximum. Depending upon this t value, you can say whether the system is fast or slow. Now if we assume t is equivalent to 0, as I've got that 1 minus e power minus t by t. If small t value is equivalent to 0, the output is 0. If t is equivalent to 1t, it is 0.632. If t is equivalent to 2t, 0. So here, as we have applied the input signal as unit step, which is having the amplitude as 1. In order to get the output signal as also 1, it actually need infinite amount of time. But if you observe here, at t is equivalent to 5t, it is 0.993, which is approximately equal to 1. Means it will take 5 time constants in order to get the output to the final value as 1. So the input assumed it as a unit step input, and the time taken to reach to the maximum value of 1 is nothing but 5t. So this is the response of first order system for a unit step. In the next class, we are going to discuss about the time response analysis of a second order system. Thank you.